Alright, here we are with Lesson 11, Ratios of Fractions and their Unit Rates. So for example 1, during the last workout, Izzy ran 2 1/4 miles in 15 minutes, and her friend Julia ran 3 3/4 miles in 25 minutes. Each girl thought she were the faster runner. Based on their last run, which girl is correct? Use any approach to find the solution. Hint, it might even be helpful to draw a clock. So note, time can be represented in either hours or minutes. So you'll be presenting your findings in your table group. So go ahead and try example 1 now in any method you would like, and then continue the video to compare your process to some example processes. Alright, you should be done with example 1. So you could do a table. In this case, you could do a table about Lizzie, mentioning the time, what it is in hours, and also the distance. And you can compare that to Julia. So here's one way of figuring out if the girls are at the same rate or not. So our discussion for this, when looking and comparing the tables, it would appear that Julia went farther. So this would mean that she ran faster. Is that assumption correct? And explain your reasoning. Well, by creating a table of equivalent ratios for each runner showing the elapsed time and corresponding distance run, it may be possible to find a time or distance that is common to both tables. We can see if one girl had a greater distance for a given time, or if one girl had a lesser time for a given distance. In this case, at t equals 75 minutes, both girls would have run 11 1/4 miles, assuming constant speed. So how can we use the tables to produce, or the tables produced to determine the unit rate? Well, since we assume distance is proportional to time, you can find the unit rate or constant of proportionality by dividing the distance by the time. If you use time in hours, then you will find the unit rate in miles per hour to be 9. If you use time in minutes, then the unit rate in miles per minute would be 3/20. You may have chosen to calculate the unit rate for each of the girls. To calculate the unit rate for Izzy, you would have divided the distance run by the elapsed time, which gives us a ratio 2 1/4 over 15 out of 60, which is 9. To find the unit rate for Julia, you would have divided 3 3/4 by 25 out of 60 and arrived at the unit rate of 9 as well, leading you to conclude that neither girl was the fastest. We all agree that the girls ran the same rate. However, some of you identified the unit rate as 9, while others gave a unit rate of 3/20. How can both be correct? Well, time can be represented in minutes. However, in the real world, most people are comfortable with distance measured by hours. It is easier for a person to visualize 9 miles per hour compared to 3/20 of a mile per minute, although it is an acceptable answer. Well, how can you divide fractions with a picture using a bar model? Well, you would make 2 whole blocks and a 3rd whole block broken into fourths. Then divide the wholes into fourths and count how many fourths there are in the original 2 1/4 blocks. The answer would be 9. So here is an example. The green blocks are the original 2 1/4 blocks, which is the first diagram, and divide the whole blocks into 1/4, which is the second diagram, and then count up how many blocks are there. The green blocks would equal 9. So here's another example. 1 3/4 divided by a half. We would make 1 3/4 blocks represented by the green blocks. Then we would divide them into halves. Then the number of halves that are shaded are 3 1/2. So 1, 2, this is 3, and this would be a half of a half. Here are some equations that you can do. If distance is equal to the rate times the time, then 2 1/4 is equal to whatever the rate is times 1/4. When we do the math, we would end up with the rate being 9 or 9 miles per hour. If you do the same thing with Julia, you would end up with the same thing, 9 is equal to r. So what assumptions are made when using the formula in this problem? Well, we are assuming the distance is proportional to time and that Izzy and Julia run at a constant rate. This means they run the same speed over entire time, not slower at one point and faster at another. You may have also decided to draw a clock. Here is a possible explanation. For Izzy, every 15 minutes will give 2 1/4 miles. Therefore, if we divide the clock into 15-minute intervals, then we can add the distance for each 15-minute intervals until we get 60 minutes, which is our unit rate, since 60 minutes is 1 hour. For Julia, we are given 3 3/4 miles for 25 minutes. So we divided the clock into 25-minute intervals. This will give us 50 minutes. For the remaining 10 minutes, we break it up into 5-minute intervals. To figure out the amount for each 5-minute interval, we found out how much one 5-minute interval was when given 25 minutes is equal to 3 3/4. We find that one 5-minute interval to be 3/4 of a mile. So here is a picture. If we do 2 1/4 all the way around, then that equals 9. If we break it up into 5 minutes, then 3/4 all the way around here would be 9 also. You could also do a double number line approach. How do you find the value of 5-minute time increments, and what are you really finding? So in this case for Izzy, if we count by 15 minutes, we would be at 11 1/4. If we count by 25s, and we're finding a common denominator or a least common multiple to be 75, we would also see that in 75 minutes they ran 11 1/4 miles. So to find the value of a 5-minute increment, you need to divide 3 3/4 by 5, since 25 minutes is 5 5-minute increments. This is finding the unit rate for a 5-minute increment. So why were 5-minute time increments chosen? Well, 5-minute time increments were chosen for a few reasons. First, a clock is broken into 5-minute intervals, so it may be easier to visualize what fractional part of an hour one has when given a 5-minute interval. Also, 5 is the greatest common factor of the two given times. What if the times had been 24 and 32 or 18 and 22? Well, if it were 24 and 32, then the time increments could be 8-minute intervals. This is because 8 is the greatest common factor of 24 and 32. If the times were 18 and 22, then the comparison should be broken up into 2-minute intervals, since the greatest common factor of 18 and 22 is 2. All right, let's take a look at example 2. This is your first experience evaluating complex fractions. Evaluating complex fractions is just like dividing fractions. Keep in mind that the solutions shown here are not the only way to solve these problems. This example asks Meredith to determine the unit rate expressed in miles per hour when a turtle walks 7/8 of a mile in 50 minutes. In order to determine the unit rate, we will again divide the distance by the amount of time. We see that Meredith represented her calculation with the fraction 7/8 over 5/6. This is called a complex fraction. A complex fraction is simply a fraction whose numerator or denominator, or both, are fractions. Can you recall what operation the fraction bar separating the numerator and denominator represents? Well, that would be division. So therefore, Meredith is actually dividing 7/8, the distance the turtle walked in miles, by 5/6, the amount of time. The complex fraction represents the division problem using fewer symbols, but the operation always remains division. So let's answer part A. How is the fraction 5/6 obtained? Well, since the unit rate is expressed in miles per hour, 50 minutes needs to be converted to hours. Since 60 minutes is equal to 1 hour, 50 minutes can be written as 50 out of 60 hours, or 5/6 hours. How can we determine the unit rate? We need a denominator of 1 hour. Right now the denominator is 5/6 hours. We can multiply 5/6 by its multiplicative inverse, or the reciprocal, 6/5, to determine the denominator of 1 hour. So using this information, determine the unit rate in miles per hour. Alright, you should have figured out the unit rate. By multiplying by the reciprocal, we get 42 out of 40, which reduces to 21 out of 20. So the turtle's speed is 21/20 miles per hour. Alright, let's do the exercises. Complete the exercises on the lesson worksheet, continue the video to check your answers, and write any questions down to bring to class. Alright, you should have finished the exercises. Let's check your answers. Make sure you pause the video and check your work against the work here, and if there's any questions, write them down so you can bring them to class. Alright, let's wrap this up. Answer these questions in your own words. Can you give an example of when you might have to use a complex fraction? How is the unit rate calculated? Can we calculate unit rates when both values in the ratio are fractions? How is finding the unit rate useful? Alright, we'll see you in class.